Hi everybody, this is Dr. Hammond for Physics at University of Windsor, 3210, electromagnetic waves. A lot of you send me emails asking about the final poster project, so I thought I would post an example of it online. This was something that I'd been working on the other day. And I was kind of setting up a template, and then I realized I thought this was a problem that warranted further investigation, but nobody actually picked up on this. Nobody picked this subject, so I decided to answer it myself to see what I could do. So I've obviously worked through the analytic solution before, but I haven't really tried to solve this computationally. And I was already developing some ODE solvers, so I thought maybe I would try my hand at this. So I'll talk a little bit about this poster, but I'll also talk about how the marks break down in this as well. So I have this poster on Blackboard, so you guys can download it, but I can also walk you through these points as well, since I would normally be going through this in class, but we don't have class, so I thought I would just post this for you to be able to view. So of course, you could download this template. So it's a PowerPoint template. It's 4 feet by 3 feet. That's kind of a standard poster size. You'll want to have like the institute that you're from, so University of Windsor, or at least like the symbol, of where you're from. You might want, if you're working in a lab, something like that. You'd also have, maybe if your lab has a slogan or something like that. That's something you can do. The old lab that I worked at was a joint attosecond science lab, and so it had the acronym JASS Lab and it had its own little symbol. So we had, University of Ottawa and NRC, and then we also had this JASS Lab. If you have any funding, so for those of you who might have a USRA scholarship for in the future, so if you're doing, this for You Will Discover or another conference or something like that, you'd also have like the funding that this is from. But in this case, this is just for a class, so we just have this for University of Windsor. And then, of course, you need to have a title. I thought since radiation reaction already has alliteration, I figured I would just go with it and make a terrible title. You of course want to have your name, and you would probably normally have like the research group that you're from in here, or maybe like a supervisor's name, or other people who have contributed to the poster or something like that underneath. But since all these posters are being done individually, I just thought we'd say that this is for electromagnetic waves. So of course you need to have an abstract. Ideally you'd probably have a little bit more space for an abstract, but having something fairly short is good. For those of you who did submit something to You Will Discover, I think we have about 250 words for your submission. This is, I'm not sure, maybe something like 80 words or something like that. So it's a little on the short side. You'd probably want to have a little bit longer. The abstract, as I have listed here, it's worth 20 points or 20 marks. As I say in my comments, the main findings should be given in the abstract. I'm a little vague with what I found. This isn't a particularly good abstract. It's a little short. I should probably have, talking about the two cases of having runaway solutions or acausal acceleration. But unfortunately, as I set this up, I put the abstract in last, so I was a little bit tight for space. So I would definitely dock marks for such a bad abstract. For those of you who are wondering how I'm going to be grading this thing, this would probably be, maybe 15 out of 20, maybe 14 out of 20 or something like that for an abstract. It doesn't have any, definitive conclusions. You want to have something a little more definitive than this in here. You definitely want to state some of the main findings, which I don't do. All right, so onto the introduction. Introduction is 10 points. You want to introduce the problem. So I discuss, the source of radiation is an accelerating charge. And then I kind of go a little bit off topic. This classical prediction is a consequence of Maxwell's equations. As we now all know, Maxwell's equations predict that an accelerating charge is the source of radiation. But this is actually fairly inconsequential to what's going on. We don't further talk about Maxwell's equations in this. It is important to talk about the power that's radiated from an accelerating charge. So that's important, but the fact that we're talking about Maxwell's equations is actually kind of an aside, and when we're tight for space like this, we're not really making a good use of space. So I'd like you to think about that when you're designing your own paper or your own poster. For theory, this is worth 30 points. So you want to give a little bit of, you know, kind of a very basic theory. You don't want to get into the full details of this. So normally when you'd be presenting a poster, you would be kind of standing by it. So this is kind of just giving a rough rundown of, you know, some of the math that's going to be behind this. And so I say, you know, well, I've already talked about power. We have power, well, we have energy here, and we want to go from energy to force. So that's what I'm kind of trying to link between equations 1, 2, and 3. Oh, I guess this third equation, I should have these aligned properly. That would look a little bit nicer. But that's the point of having the, you know, this force is the thing that I actually care about here, this radiation reaction force. And so I kind of give inspiration by saying how the force comes from, is related to energy, and energy is related to power. So that's kind of how these are all related. The one thing though is that this paragraph here is actually written quite poorly. This is written at kind of an elementary school level. This should probably be rewritten with a little bit more thought. And then here I go into actually talking about how this differential equation that we're going to need to solve. The problem though is that I actually already say, like, you know, F equals ma, and then I have this correction to Newton's law saying m tau a dot. The problem though is that tau is going to be this stuff out front divided by m, but I don't actually define it anywhere, and that's actually a huge mistake. If you introduce something and then don't define it, that's a serious mistake. So for this introduction here out of 30, I would immediately deduct 5 marks if I haven't defined something that I'm using. Maybe even more. And then I also have a typo. This should have a period at the end of this because it's completing a sentence, and then this should be a capital letter here, but I don't do that. Then we get into the numerical model. I solve this differential equation using the step function, and I show that this leads to a runaway solution. I guess I should say the results are they're worth 40 points. And same with the discussion, they're also worth 40 points. So the most of the stuff is going to be, most of your marks are coming from the results in the discussion. About half of the marks come from results in discussion. So for these results, I end up doing the numerical model. I solve this differential equation numerically. But the thing is that this first one can be solved analytically, and I give an runaway solution. And then the second one, I say, oh, well, what happens if we, you know, instead of having this sharp, sudden on and off force, we actually have this kind of more gradual, slightly more gradually turn on and turn off, and what happens to the answer. But it turns out this also leads to a runaway solution, and so there's not really any difference between these two. So there's not much insight that you get from having two plots that basically look the same. And so, as I said before, this is fairly tight for space. This isn't really good use of two plots. Talking about this is okay, but then the thing is that this main section of this poster is all writing. And so what I want you to do is, if you're walking down the hallway, to kind of catch a glimpse of something and say, oh, this seems interesting. I want to have a little bit closer look at what's going on here. And I have, you know, like a caption for these figures to say, you know, what the differences these are. But I should probably have something like sudden field switching and slower field switching that leads to runaway solutions or something like that. And so just so that people just reading that caption and reading these things know that there's a problem that needs to be solved, kind of thing. But I don't. So it's not perfect. And this thing, yeah, the main chunk of this poster is all writing, which is also not great. It should be more pictures to like grab people's attention. Having an analytic model, you know, I have a few equations, and I can say, you know, what the difference between this this runaway solution is and this analytic solution where we get this acausal acceleration. That's kind of mentioned down here, leading into here as well. And so this is part of this discussion is now I talk about, instead of this runaway solution, we're discussing this acausal acceleration, which is, you know, a big no-no in physics. It's violating a fundamental tenet in physics that, you know, things have causes. They're, you know, action reactions. So as I said before, the discussion is worth 40 points. These figures aren't substantially different. So this is the analytic solution using this integration constant for the acceleration to avoid the runaway solution. But this has this acausal acceleration. So before this pulse is even turned on, this thing starts to accelerate. And then before this pulse is even turned off, this thing starts to decelerate. And then, you know, it acts like it doesn't end up having some acceleration afterwards. Whereas these just integrate, or these just accelerate for infinity, and then they end up, you know, flying off at the speed of light, which is absolutely insane. It turns out you can also do this numerically if you change your initial conditions. If you give this thing just the right acceleration to start, then you can actually have this, you know, no, you don't have that final acceleration, but it means that you have to have some acceleration at, you know, t equals minus infinity, which is the thing that's kind of insane. It's acausal. But again, these two plots are basically the exact same thing. They should in fact be the exact same thing, except that one's analytic and one's numerical. So there's really no difference, because it's not questioning whether or not the analytic solution is the right thing. What we're questioning is, you know, what happens if we don't have the sudden turn on and sudden turn off. That's not possible to solve, or that is possible to solve analytically. But if we have the slow turn on and slow turn off, that's not possible to solve analytically. And so that's where the numerical integrator, you know, would shine. That would be more important. So that I feel like that should be highlighted here instead. Something that I did see that's maybe mildly interesting is if we turn this on and turn this off at a slower rate, then we can see that there's this acausal acceleration, so it leads this by about 5 yoctoseconds, I should say. But you can see that they basically follow each other quite well. And so what I was finding is that if you take the Fourier transform of this, because this is so sudden, you know, this is instantaneously it's turning on, instantaneously it's turning off. If you take the Fourier transform of that, the Fourier transform ends up having, like, if this were, say, an electric field, you would have, so as I defined it here, it's an electric field times this charge. So we have like an electron, and then all of a sudden we turn on this electric field. But this switch on and switch off is so sudden that it actually acquires a large amplitude of gamma radiation that is on the order of hundreds of mega electron volts, which seems a little bit insane. And in fact, I think as far as I know, there's no like naturally occurring gamma rays of hundreds of mega electron volts. I think maybe a decay of like, you know, top quark or something like that, because the rest mass of it is high enough you can get something like that. But in terms of actually gamma radiation from like, you know, normal nuclear decay or something like that, it's much less than that. So you can generate gamma radiation that's this high, but the thing is that what you're looking at is actual like like decay of very heavy particles. And so what I kind of pontificate here is maybe since an electron only has a rest mass of half an MeV, maybe we can't turn on and turn off a field that can actually control an electron that has radiation that's greater than half an electron volt, or half a mega electron volt, or a mega electron volt. And so that's what I try to do here, but it turns out that with the numerical integration routine that's that slow, the initial conditions in order for that to work actually end up becoming too sensitive, and I couldn't end up getting that to work. So I just kind of like pontificated here and say that a pulse that has to have a bandwidth that's less than the rest energy of an electron, which kind of makes sense, because if we end up having a photon that has more than enough energy to even create an electron and positron pair, then why would we even be moving an electron with that? It wouldn't have already created an electron and positron hole, or electron and positron before even acting on the electron. So that's kind of my maybe a way around this kind of conundrum, that we seem to have a runaway solution when we have a field that suddenly turns on and suddenly turns off. It's like, yeah, that doesn't look very good, but the problem is that there is no such field that can turn on and turn off suddenly, and still actually, like, interact with an electron, is kind of my idea. So I kind of mentioned that, but I don't really make a very strong argument about that, and so my comment is I don't think this is correct, because there's a lot of conversation about that seems to be requiring like quantum field theory and things like that, which this poster does not delve into. So anyways, that's basically why I say I don't think this is correct. And I mean, I don't know how I would mark that, but I would probably take off a few marks for something that's so not substantiated. So conclusion, I'm only making like 5 points for conclusion, because you've already made your argument, you've already modeled this, you've already have an analytic solution, you've already shown all the results. Basically the conclusion is just like, this is what we showed, and that's about it. And then yeah, I just say, like, can this have any other consequences? The conclusion, it just needs to summarize kind of what we've seen. And then references is also 5 points. So just having references, basically, I don't really care of a style guide. You can do them however you want, as long as I would be able to, see the reference and be able to Google it and quickly find it. If you just had, say, Griffiths as a reference, I would have no idea what you're talking about. Obviously, having the textbook is good, and then having the edition and when it's published is good. But I expect more references in this. So this is just citing the one textbook, but because, say for example here, this should really require some quantum field theory, I should probably have looked up, a quantum field theory paper or something like that. But this took me, just a few hours to do this, whereas I kind of expect from you guys, as I said, 15 to 20 hours. So I expect you to be able to find a couple of references that support your arguments, maybe another textbook or some papers or things like that. But anyways, this is how I would analyze this poster. So for those of you who are asking, what kind of what I'm looking for in a poster, I would say overall this is about a B+. It's fine, it's decent. Things could be better though. So if you guys are kind of wondering how you would do, if you want to get better than a B+, then I would recommend taking some of these suggestions that I've said for how to improve this poster and use those. And if you have any questions, feel free to email me. If you're working on a draft, feel free to send that to me so we can kind of discuss, what might be important aspects of your project and things like that. You don't have to, you have about 3.5 weeks to work on this thing. You don't have to be working completely on your own in the dark on this, and then, just submit it to me at that last minute. I'm very happy to work with you guys on this throughout the process, so we can make this to be, the best thing that you can possibly do. All right, and with that, I think I've analyzed this well enough. I've also uploaded the PowerPoint so that you can use that as a copy. Feel free to change, the background color, whatever it is. I kind of use these boxes so that the text is kind of highlighted and like shows how those different sections are, kind of like emphasizes the different sections and things like that, but feel free to do this anyway. You can have this on a white background, I don't care. You can, do it however you want. Some people even like having posters run vertically, so instead of being 4x3, they're 3x4 or something like that. I kind of like that look, maybe preferable. I might prefer that look, but sometimes it doesn't, they normally give you kind of a 4 foot by 3 foot poster board, so that's why I went with this. Yeah, so feel free to change the layout however you want, but this is just, for you to get started. All right, and with that, I think we'll go back to notes.